So let's move to what is called Low-Reynolds number, that is LRN models. As I mentioned, Low-Reynolds number refers to the locally Low-Reynolds number in a turbulent boundary layer, right? So near wall region is very important. Capturing near a wall, capturing near wall region is important, and that means you need to have a mesh guidelines for this. So the mesh guidelines will be like this. Mesh guidelines. So you need to have a mesh, say you have a wall, so you must have grids like the first one should be y plus less than or approximately equal to 1, the first node or the first node above the wall. So there will be another node on the wall for boundary condition, or it will be inside the wall if you are using a ghost node implementation, that is in the CFD framework. In general, let's say you have a node on the wall. So this first node above the wall, y plus less than or equal to 1 must be there, and you must have about 5-10 nodes. 5-10 nodes must be there in about y plus less than approximately equal to 20. So within 1 to 20 you must have at least like 5-10 nodes, depending on your exact problem, how challenging it is. You can vary this, okay, more the better, depends on how many nodes you can actually account or accommodate for, depending on your computational resources. So this is the mesh guidelines or grid guidelines. So the objective, now I'll come to what we have to do it for introducing a damping function. So the objective of LRN model is that the exact equation of a turbulence kinetic energy and the modeled equation of the turbulence kinetic energy must behave similar as we approach the wall. Okay, so near wall behavior of both the terms, because we have modeled certain terms making some certain approximations, that we have to see whether term by term they are having same behavior, near wall behavior. Okay, so the modeled equations of, let's say, k, epsilon, omega, whatever you have, okay, should behave the same way as exact equations as we approach wall, that is as y tends to 0, the behavior of these two should be similar. The exact modeled equations, model terms and the exact terms must have the same, otherwise you need to introduce this damping function or some corrections so that the behavior is same as we approach close to the wall, and we see that this is not the case. So in general, not in general, the eddy viscosity models do not account for this. So the model terms are different than the exact terms that we see. So but this will not be the case, since models assume turbulent condition even in the sublayers, that is your linear sublayer. So whenever we are using eddy viscosity model, we are computing eddy viscosity everywhere in the fluid, buffer layer, linear inertial sublayer, as well as in the linear sublayer, right? And we don't have access to Reynolds stresses, which actually goes to 0 on the wall, we have replaced Reynolds stresses with a Boussinesq, which depends on velocity gradient, right. So the behaviors are very different of Reynolds stresses and its modeled counterpart, which is strain rate, right. So that we will see. So basically what we want here, that is model term and exact terms having same behavior, will not be there by default, because this will not be the case since models assume turbulent condition even in the sublayer. So now we see what these two terms should look like. Okay. So now let's take a look at each of these fluctuations as we approach the wall. For that we will do a Taylor series expansion. So a Taylor expansion of fluctuations near the wall. So that means, let's say u prime at some y very close to the wall will depend on u prime at y equal to 0, y 0 plus you have du prime by dy y raised to 1 plus du dou square u prime by dy square y square plus higher order terms. So here I can take this u prime, du prime by dy and all this derivative terms as some kind of a coefficients which are functions of time and space. So let's call this, I would like to call this as A0, A1, A2 and so on. Okay. So note here that A0, A1, A2 etc. are functions of space and time. That is your velocity fluctuation and its derivatives, higher order derivative terms. Okay. So now I can write the equation for u prime as basically A0 y0 plus A1 y1 plus A2 y square and so on. Similarly v prime, I will use B0 y0 plus B1 y1 plus B2 y square, higher order terms. Similarly W prime, the wall parallel fluctuation, which is C0 y0 plus C1 y1 plus C2 y square, and the higher order terms. Okay. So now at the wall I can apply a wall boundary condition for this. So for u prime and w prime, wall parallel fluctuation, and v prime wall normal fluctuation, I have both no slip and kinematic boundary condition. So if I apply boundary condition, applying boundary condition on the wall, what do I get? So I have this no slip comma kinematic boundary condition. So basically u prime is 0, u prime, v prime, w prime is 0 on the wall, right. So u prime at y equal to 0 equal to v prime at y equal to 0 equal to w prime at y equal to 0 is 0, which implies A0, B0, C0 is 0. The first one is going away. Also on the wall, the wall parallel gradients, that is you have du prime by dx at the wall y equal to 0, right, equal to w prime by dou z at the wall y equal to 0. The second component where a1, b1, c1 is coming, dou u prime by dou y, dou v prime by dou u prime by dou y, and the other components. So this on the wall here, this is also 0 here. On the wall, I am looking at on the wall, right? So in CFD terminology, let's say you have a wall, right? And then I have nodes. If you can think about this as your P node, east node, west node. Now look at the gradient dou u prime by dou x on the wall is 0. Similarly, dou w prime by dou z. Only the wall normal gradient exists, right? Dou u prime by dou y and so on exists, but the wall parallel gradients are 0. So if this is the case, then what happens to the other one? By continuity we can get, right? So by continuity equation, dou v prime by dou y equal to minus dou u prime by dou x minus dou w prime by dou z, which is equal to 0. So what does this imply? Where does this dou v prime by dou y comes? That is b1 equal to 0, right? So I have, this implies b1 equal to 0. b1 here, b1, which is dou u prime by dou y, right? So I have b1 equal to 0, these three equal to 0, a0, b0, c0. So what will happen in, let's call this equation 1. So equation 1 reduces to u prime equal to a1 y plus and so on, which is a1 y plus a2 y square plus higher order terms. So that means to first order it is behavior is y. So u prime behavior as you approach wall depends on y itself, right? Order of magnitude y behavior as you approach the wall to first order. Ignoring the higher order terms. So v prime, b0 is 0, b1 is also 0. So it is b2 y square plus, it is showing a y square behavior, right? We don't even have to look at the data. Even here we are seeing that the wall normal fluctuation is having a y square behavior, but the wall parallel one u prime is having a y behavior, okay? Similarly, w prime is your c1y plus c2y square and so on. So it's of the order y. So this is having a different behavior here, y square behavior, indicating a two component limit, a different behavior, right? So a y square behavior here, you can say it's a two component behavior. It is kind of damping as y square. As you approach wall, the u prime and w prime damps as y, but v prime damps as y square. So there is a faster level of damping here, even in the equation, just by Taylor series expansion. Okay, so now what did I say in the beginning? The objective is to look at modeled equation, all the term by term in the modeled equation and the term by term in the exact equation, the counterparts of two equations, and we see from these two what are the whether they have the same y behavior or y square, y cube, what kind of behavior they have between the two terms, exact and its counterpart in a modeled equation. For that we need, of course, to know the behavior. We have the behavior of this u prime, v prime, w prime. So now we can go ahead and get the behavior of other terms very easily. Okay, so for example, we can look at the stresses. So stresses are occurring in the production rate of turbulence kinetic energy in the exact equation. You have uij prime, ui prime, uj prime average. So all the stresses are occurring. So let's see that behavior of u prime average. So what is u prime? U prime itself is a1y plus a2y square and so on. So this will be a1 square average y square plus higher order terms. I am simply multiplying u prime. U prime was a1y plus so on. So it was a1 square. A1, if you recall, it is nothing but your u prime, right? So it has to have your a1 is basically dou u prime by dou y, right? So it's a fluctuating quantity. So it's a average of a correlation, functions of space and time. So a1 square average y square and so on. Similarly, I get, so this of course will have behavior of y square. Okay, so v prime average, this, the smallest term here is b2 square, right? V prime is b2 y square plus higher order terms. So that means this becomes b2 square average y raised to 4 plus higher order terms. So this has a y raised to 4 behavior, the wall normal stress. And w prime average is giving me c1 square average y square plus higher order terms. So it is giving me a y square behavior. And then the shear stress u prime v prime, if I take this, I would get, of course, one u prime has a y behavior and v prime has a y square behavior. So this will give me a y cube behavior, right? So this will give me a1 b2 average y cube plus higher order terms. So this is giving me a y cube behavior in the near wall region. Okay, so we have the Reynolds stresses, and we also need turbulence kinetic energy because that appears in the diffusion rate and so on. So the turbulence kinetic energy K will be essentially half of your u prime plus v prime plus w prime average, the first three components. So that means it will have essentially half of your y square plus b2 square average y raised to 4 plus c1 square y raised to y square higher order terms. So this is giving me a y square behavior only. So turbulence kinetic energy is giving a y square behavior to first order. Okay, so what else we have? We have we also have the mean gradient, right, in the production rate of turbulence kinetic energy Pk, Reynolds stresses multiplied by dou u bar by dou y and so on. So we have that term also. So dou u bar by dou y term. Before that we can say what is the dou u prime by dou y term. This occurs in your dissipation rate of turbulence kinetic energy in the exact one. Dou ui prime by dou xj square average, okay, multiplied by kinematic viscosity there. So dou u prime by dou y will give me, if I differentiate the u prime, I would get basically a1 plus higher order terms. So I have y0 behavior, dou u prime by dou y. Similarly, dou u bar by dou y will also give me the same one, a1 bar plus, so I would get y0 behavior as well. That is no y dependency. Basically it is telling me these two components have no dependency on the y at all. Okay, and then I have epsilon, which is the dissipation rate. This one is the exact one. If you recall, I will have nu dou ui prime by dou xj square average. So here to first order, as I said, dou by dou y terms we are looking into. Essentially, this will be a function of dou u prime by dou y, dou u prime by dou y. This will be a sum of course 9 different terms. Okay, so we will have this, but to first order, if you take it up, it essentially comes to u prime, dou u prime by dou y dependency. The others are higher order terms. So this will give me again no y dependency for an epsilon also. Okay, and then what else I have? I have dou k by dou y term. This comes in the diffusion rate, dou k by dou xj, right? I'm looking into only this y because I'm going to take up a statistically stationary and homogeneous in the two direction, that is a plain turbulent coed flow. If I take it, then dou by dou x, dou by dou z terms vanish. So only this dou by dou y terms become dominant. So I'm looking into only that part. So dou k by dou y. So k has y square behavior. So this will give me y behavior, y dependency for the dou k by dou y term. And then apart from this, we have the in the model term, of course, the d viscosity is also there, that I will see. I also need what else I would need? The triple velocity correlation. So the p prime ui prime over bar, the pressure diffusion rate is not modeled. If you recall, we said this is small in certain class of flows, so we did not model, and therefore its counterpart doesn't exist in the model equation, so we will not consider that. So we are in the diffusion, we are looking into only viscous diffusion and turbulent diffusion and its counterpart in the model. So viscous diffusion will have this dou k by dou y, new dou k by dou y term will come, okay, and the other component is the turbulent diffusion rate. So the turbulent diffusion rate is, let's say, the v prime ui prime let's say. This will give me the behavior of v prime is y square behavior, and this one, each one will have ui prime, that is the sum of this particular thing is giving me to first order only turbulence kinetic energy behavior, ui prime. So this gives y square behavior, this is giving me y square behavior. So this gives me essentially y raised to 4 behavior. This is like turbulence kinetic energy, this part. Okay, so we will use all these terms and substitute it in the equations to see whether the two terms have same y dependency as you approach the wall. If not, which is the case, then we will see what has to be done in the next class. Okay, any questions on this so far? We will take it. Yes.